Malibu. Apology, yeah. I haven't listened to it on yet.
However, with this kept showing a screen to me, and
Come on, I'll listen to the album. I was like, I'm only halfway, and it's been like half an hour, and like, how long is it?
well, when you have like an album or you like it a lot, it goes pretty fast.
That sounds pretty good.
All right. Got a lot to cover today. So this morning, started covering some specific events within the Cascade Volcanic Range. Yesterday afternoon was all about the entire range, and today is about specific things. Oh, let me take attendance. Here we go. So basically the order of operations here, I'm going to finish up talking about specific events. Covered 3 of them this morning. If you didn't tune in, check it out on the YouTube channel. I'm going to post links to specific lectures on the Google Classroom so they're easy to find. So we covered 3 of them this morning. Mount St. Helens, May 18, 1980. Mount Lassen, May 22, 1915. And then Mount Rainier, 5,600 years ago, 5,600 years ago. The big deal with Rainier, I've got some slides to show here in a little bit. The big deal with Rainier was the Osceola mud flow, this gigantic mud flow that made it all the way to the Puget Sound. So all the way from the mountain, something like 50 to 75 miles down river valleys, all the way to the Puget Sound in Tacoma, Washington. That's got some pretty serious implications, right? If Mount Rainier erupts again, and it makes another one of these mud flows, it would take out significant populated areas. So the 4th and final specific event that I wanted to get to this morning that I just didn't get to was 7,700 years ago. And Mount Mazama is the name. It's kind of weird because today it's called Crater Lake. But the name we have for the actual mountain and the eruption is Mazama. That is down here in southern Oregon. And this was a big eruption, big eruption. So basically, Crater Lake National Park, maybe a better way to say this, Crater Lake National Park sits in the crater on top of Mount Mazama, but everybody just calls it Crater Lake. This was a much larger eruption than Mount St. Helens. And Mount St. Helens deposited a couple inches of ash particularly in eastern Washington. But Mount Mazama made ash deposits that are over 1 foot thick. And so much ash that, even here in Mattawa, in eastern Washington, we're like ground zero for Mount St. Helens ash. And Mazama ash deposits here are thicker than Mount St. Helens ash deposits are here. Mazama deposited ash on a really wide footprint of the map, and because of that, it's a really important marker bed. Marker bed. What does that mean? That means it's if you can find Mount Mazama ash, you have a solid date. So geologists look for Mount Mazama ash to date other events. So it's a pretty important marker, and because the ash from this volcano covers the entire west coast of the United States, it's a good marker bed for correlating events. Correlating some rocks here on the Olympic Peninsula with some rocks down here in California, we can figure out if they're related if we can use Mazama ash as a marker. I said much bigger than Mount St. Helens. How about 43 times bigger? 43 times. Mount St. Helens was 1 cubic kilometer of material. Mount Mazama was 43 cubic kilometers of material. So, big deal. Now, some of the questions that often come up are, so do we need to be worried about these things? Do we need to be afraid that one of these 4 is going to erupt again? Or what about one of these ones that's been sitting there and hasn't erupted in a while? And the answer is no. We don't need to be afraid of volcanoes. Because, for one thing, the Cascade Volcano Observatory is a branch of the USGS, United States Geological Survey. And there is so much equipment deployed on the flanks of every one of these volcanoes. There is all kinds of seismic equipment and other ways that they monitor these volcanoes. And so there are always signs. They don't erupt out of the blue. They slowly wake up. Like with Mount St. Helens, there were earthquakes leading up to the eruption. As the magma got closer to the surface, the volcano warmed up and a lot of the snow and ice started to melt off of it. So there are signs, and geologists will know before any of these actually does anything significant. Three Sisters down here in Oregon, it's actually 3 volcanoes in one. Three Sisters has been showing signs of activity over the last 10 years or so, kind of inflating a little bit. But nobody's concerned about it yet. I did some work with one of my undergraduate classes. We did some work at Three Sisters, went down and deployed a bunch of GPS equipment and collected data for a week, and then went back and collected it again. If I had more time, I would tell stories from that, because that was a really cool class and a pretty wild couple of weekends. But let's see, I'm gonna try to dial up this slideshow and go over show you a couple of the things some pictures to go with some of the things that I told you. I'm going to do it. That one. This one. Not that one. This side, screen mirroring. Room 43. I'm really good at this. I would have all of this stuff all set up when you guys came in the room. Room 43, let's go. 1680, there we go. And okay, this is just an awesome picture. There's like 5 Cascade volcanoes: St. Helens, Rainier, Adams, Mount Hood, and Mount Jefferson. So this is a picture from the air over Oregon, looking north. There's Mount Rainier. And so the point of this picture is to show how many people live pretty close to this thing. There's Mount St. Helens, gigantic crater. And this morning the number was 1,300 feet off the top of this mountain. So before it erupted, it would have been something about like that. Inside here, right about here, there's actually 2 different lava domes. There's one about like that, and then there's another one about like that, that are actively growing, rebuilding the mountain. And someday, in thousands of years, it will get back up to its former glory, no doubt, or it will erupt again. There's Crater Lake. That's Mazama, Mount Mazama, the top of Mount Mazama, and the hole in the ground, the big crater. This little island is also a lava dome. So after this one erupted 7,700 years ago, it had a lava dome begin to form like Mount St. Helens. This is a good poster. I've seen print versions of this. I sort of like to have a print version of this. 4,000 years of Cascade volcano history, and the number of eruptions. So Crater Lake, it's been inactive since its most recent one, 7,700 years ago. Jefferson, as well, has been inactive for at least the last 4,000 years. Lassen has been active recently, but it was quiet for 27,000 years before that. There's Mount Shasta. It erupts pretty regularly. Medicine Lake, it goes in spurts, like coupled and a long quiet time, then a bunch, and then more quiet time. Newberry, not very often. Mount St. Helens, that is a busy freaking volcano. We've got what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 Mount St. Helens eruptions in the last 4,000 years. Rainier's pretty dependable too, although it's been slowing down. Baker, not much at all. So different volcanoes, and I don't know the individual ages of these mountains. I should know that. Could it be that Mount Jefferson is one of the older ones and approaching the end of its 2 million year lifespan? Possibly. I don't know. This is another good graphic here to get a sense of relative volumes. Here's Mount St. Helens, 1 cubic kilometer. And if this little yellow cube is Mount St. Helens, here's Mount Mazama. Here's the most recent Yellowstone eruption. Give you a sense of what those supervolcanoes can do. Here's the Yellowstone eruption before that, and here's the one before that. So supervolcanoes are significantly, it's a whole different animal than Mount St. Helens, which is the one we're familiar with. There's Mount Lassen. I like this picture. 1914, with the Model T Ford there. Like I said this morning, Mount Lassen was the first time anybody realized there were active volcanoes in North America. There's Mount St. Helens. There is the aftermath of a lahar, a volcanic mudflow. That is after the Mount St. Helens eruption. So this is after all the dust settles, everything slows down. This is what lahars can do. And this is, I believe, the White River, and that is Osceola mudflow deposit from Mount Rainier, 5,600 years ago. And why did I pick that picture again? Why did I pick that picture? Probably to show how thick this mudflow was. We can see big boulders toward the bottom of it. They're more dense, they sink to the bottom. And as you move up, it gets finer. But this is the picture we want is a wall of boiling hot concrete traveling at 60 miles an hour down river valleys. More Osceola mudflow. There's a map. Mount Rainier. Here's the Puget Sound out here. Olympia, our state capital. Tacoma, the land of eternal road construction. And in color are the paths of the various lahars or mudflows, volcanic mudflows, from the most recent Mount Rainier eruption. And then color-coded, red, I assume, would mean more likely, more danger, and yellow, the more yellow it is, the less likely it would be. But it's a lot of mud, all the way covering Tacoma, covering Puyallup. Some of these other places, Ashford, Greenwater, Enumclaw's pretty close. Packwood. These are important agricultural communities. So anyways, that's how far these mudflows travel. And yeah, that was the White River, the last photo there. That's the White River, which is this one here. And those mudflows made it all the way to Tacoma. Okay, those are some slides. Here. Okay, second part of today is I gotta get to this Olympic Peninsula stuff, which we got time. If I don't dally. So Olympic Peninsula, whole different thing. We talked about Cascade volcanoes. We looked at Cascade volcanoes. When we did our Washington State Geologic Map Lab, one of those questions was, I shouldn't use red, one of those questions was about Mount Olympus. Mount Olympus. And that is over here. There's the Olympic National Park up there. It's beautiful. You should go there sometime. But it's interesting because you can ride a ferry boat. If you go to Seattle, you get on the ferry to go across the Puget Sound. You're out there on the water, and if you look to the east, you can see Mount Rainier, snow-capped mountain, blah, blah, blah. If you look to the west, you can see Mount Olympus, snow-capped mountain. So, and in fact, where I grew up in Edmonds, which is kind of right up here, and I could see from my house, I could see snow-capped Olympic mountains, and I could see snow-capped Cascade mountains. And I remember my mom telling me that those ones are volcanoes and those ones aren't volcanoes, and I never understood why. Why isn't Mount Olympus a volcano? Why aren't the Olympic Mountains a volcano? But they're not. Never have been, never will be, won't erupt, can't erupt, no magma, none of that. So we've got all of our Cascade volcanoes, right? These are all because of Juan de Fuca plate subduction. So if we have more big, tall mountains out here that are not volcanoes, then what's up with that? Where do they come from? Are they related to the Cascades? Are they related to Juan de Fuca subduction? Whole other story entirely? Give me your favorite black pen. The answer is yes. Mount Olympus and the Cascades are in fact related because of Juan de Fuca plate subduction. The Juan de Fuca plate subduction has built the Cascade volcano range, but it has also caused and built the Olympic Mountains here. So, how's this work? I'm going to draw a cross section. We'll make a little cross section. So, we'll start with our familiar subducting Juan de Fuca plate. This is a familiar part of our concept at this point. There's Juan de Fuca going down. Okay, so there's a more accurate cross-section than we have drawn to this point. Here's Mount Olympus. We're going inland. There's the ocean. So Mount Olympus, Puget Sound. There's Mount Rainier. We know why Mount Rainier is there. We know why Cascade volcanoes are there. We do some melting. We do some mixing. We mix some melted oceanic crust and some melted continental crust, and bam, we've got a composite cone volcano. So what's going on here? We're not making magma. The subducting plate is not deep enough to melt yet. So we're not making any magma. But the idea that we want here, I'm going to change this just a little bit and give myself a little bit more room. There we go. The idea that we want, and you might remember this even from the Washington State Geologic Map Lab, it had you look at what kinds of rock were here. And it was all sedimentary and metamorphic stuff. The idea that we want is that sitting on top of our Juan de Fuca plate is a whole bunch of sediment, mud, ocean floor stuff that has settled down there. And there's a thick enough layer of it to make rocks. Juan de Fuca plate's pretty old. It's an old Farallon plate. It's been around for a long time. Well, at least long enough to get from this spreading ridge to here, but that's long enough to have marine deposits. It's long enough to have sedimentary rocks forming on top of it. And the idea that we want here is that this stuff is kind of getting scraped off as the ocean floor, as the basalt ocean floor is subducting. As the basalt ocean floor goes down, all the stuff on top gets scraped off and stuck onto the edge of the continent, of the tectonic plate. So we are gaining real estate. With every inch that the Juan de Fuca plate goes down, we get some more inches of sediment scraped off onto the edge. And of course, as we scrape off all of this sediment, it's going to end up pushing this stuff up. So we end up pushing up and creating a big pile of sediment. We also, of course, we have just this relationship creates reverse faults because it's compression. So we're going to have reverse faults and thrust faults in there, which also build mountains. So we have mountains here that are made of scraped off sediment. There's a name for this. And it is called subduction complex. The subduction complex is the name we give for the big pile of sedimentary rock that forms as ocean crust is scraping down beneath the continent. You say, well, great. That explains Mount Olympus. Why don't we have Olympic mountains all down the coast here? We've got subduction all down the coast. Why don't we have Olympic mountains all down the coast? We kind of do. The Olympic mountains, let's see. I get some new oranging. The Olympic mountains, Mount Olympus is the tallest one, but we've got mountains. If you ever go out to the ocean, it involves a long, windy drive through pretty hilly spots. Those mountains kind of peter out down here, but down in Oregon, what are they called? Not the Blue Mountains; those are over there. Oregon has a coast range. California has a coast range. And we have this relationship all down the coast of maybe not quite as tall as Mount Olympus, but, reasonably sized mountains that are not volcanic. They're built of sedimentary rock. Klamath. The Klamath Mountains of Oregon is the name of it. So, there's a pattern here. Non-volcanic mountains at the coast, lowland, and then volcanoes. Right? We've got Mount Olympus. We've got the Puget Sound. And then we've got Mount Rainier. And we can generalize this pattern to say that we have a subduction complex. We have what is called a four-arc basin. Better write that out. Four-arc basin. Exactly. Four-arc basin. That's the Puget Sound. And then we have our volcanic arc. Remember, volcanic arc volcanoes, that's labeled even on your page 40 diagram. A line of volcanoes that is parallel with a subduction zone is called an arc of volcanoes. So, Olympics, Puget Sound, Mount Rainier, Cascade volcanoes in Washington. In Oregon, we have the Klamath Mountains. We have the Willamette, Willamette, I think, Willamette Valley, and more Cascade volcanoes. Coast Range, I don't know what this little valley's called, more Cascade volcanoes. Ooh, I got more time than I thought I did. This is great. What about California? We wanted evidence a couple days ago that California, before North America started crossing the Farallon Plate, that California used to, I really got to get better at the southern tip of California. I don't know how it works. We said that a good piece of evidence that California used to have Cascade-style volcanoes was that we have the Sierra Nevadas, old plumbing systems of composite cones. But I don't know if you've ever been to San Francisco. There are some freaking hills in San Francisco. And all along the coast of California, we have what's called the Coast Range. And right smack dab down the middle, we have the San Joaquin Valley, also called the Great Valley. Such an insane amount of food is grown in the San Joaquin Valley, and it's a tremendously boring drive. You road trip down through California, and Washington's beautiful, Oregon's beautiful, Northern California's beautiful, and then you hit the San Joaquin Valley, and it's like driving between Moses Lake and Ritzville for like 8 hours. It's just on and on and on, and there's nothing and nothing and nothing except for fields and so much agriculture. The Sierra Nevadas are an ancient arc volcano system. We know that based on their rock type, based on their geometry with the coast. The Coast Range is an ancient subduction complex. And the San Joaquin Valley, or the Great Valley, is an ancient forearc basin. So we can see active subduction complex, active forearc basin, active arc volcanoes, ancient subduction complex, ancient forearc basin, ancient arc volcanoes. This is one more tremendous piece of evidence to say that, yes, this did once used to be actively erupting volcanoes. The fact that we have a coast range and we have a forearc basin. We have a subduction complex and a forearc basin. One last little thing, because I got time. Little comparison here. North America, two cross sections. North America and South America. North America we have subduction complex, forearc basin, arc volcano. All that stuff scraped off the bottom. South America, if you look on Google Earth, if I had a little more time, I'd pull it up, but I don't. If you look on Google Earth, South America does not appear to have a subduction complex or a forearc basin. The Andes volcanoes in South America are pretty freaking close to the coast. And there's a reason for that. Here's our cross section of South America. I didn't do a very good job. Let's make this a little bit more shallow. Shallow subduction, steep subduction. This angle of subduction doesn't allow for there to even really be a forearc basin in South America. We still have all of this sediment on the ocean floor, and we still have all of this sediment scraping off onto the side of the continent, but the angle of subduction is such that the volcano itself is much closer to the ocean, and there just isn't room on the ocean side of that volcano to have its own subduction complex and forearc basin. It's kind of just getting scraped off right onto the side of the arc volcano. So subduction angle, which I guess we went over yesterday as well, subduction angle controls where that volcano is. And I suppose One could even probably say something about the subduction angle based on the width of the 4-arc base. Some food for thought. I never even thought about that. I just said that right now, like it just occurred to me. So, anyways, bell's about to ring. We'll have quiz number 3 on Monday. We'll have our next lab on Tuesday. I will post key key YouTube videos to Google Classroom if you want to review or study or watch any of them again. I hope you guys have a wonderful, safe weekend. Seems like half of Mattawa has COVID right now. Wear your masks, you know. Well, you got vaccinated, right?
Yeah, I got my second dose. Yeah.
How you feeling?
All right. Just a sore arm, pretty much.
Excellent. Did you get Pfizer?
Yeah.
Me too. And I was fine the next day too. My kids both got their second dose 2 days ago, and they got their asses kicked.
It only feel like a little bit like tired, but not really a big difference.
Right. Yeah, that was what I had too. It was just like a little bit low energy, and by the time I got home, it was like, yeah, I think I'm ready to just kind of sit for the rest of the day.
Yeah, that's
But
how I was yesterday.
have a good weekend.